All right. Thanks, Dennis. I'll dive right in. Like yesterday, I've got a packed talk to give. Um, so this talk is really a combination of three different problems that I kind of stumbled into while thinking about various parts of the space elevator, and they're somewhat similar, so I mashed them together. Um, Now, these are problems that ideally we'd be discovering during climber competitions as people try to build climbers that climb real tethers. But the space elevator ribbon's kind of a special thing. It's undergoes a lot of strain. It's extremely thin. It's got huge specific elastic energy. And all these things conspire in a way that the materials that we're using for the tether in the real space elevator don't necessarily bring out all the problems. And if there's one thing that I'm hoping to get out of this talk is that maybe we think more about picking ribbons that will try to tease out these kinds of problems when we do space elevator competitions to start to get teams figuring out solutions. One example of something that I see in climber competitions at ISEC, there was a climber that was using rollers on the side of the ribbon for guidance, and that's seemed to be working just fine for the relatively thick para-aramid ribbons that they were using. But if you had a ribbon 10 microns thick, I don't think that would work at all. So here are the two problems I'm going to be talking about. The first one has to do with sliding between the ribbon and the wheels as the climber climbs it. The second one has to do with wrinkling of the ribbon when it goes through rollers. And the third one has to do with the ribbon buckling when you start to twist it. Let's start with the first problem. So first of all, like I said, there's huge elastic energy in the tether when it's under strain, 1.8 megajoules per kilogram. Compare that to the specific energy of TNT. You're at a factor of 2 away. If you were to convert that energy into heat and let it just heat up the tether would reach 5,700 degrees Kelvin. As you're climbing at 200 kilometers per hour, that's 1.1 megawatts of power that's being released by the tether. So it's a pretty large amount of energy. Where does that energy go as the climber's climbing? Well, if in the ideal case, it would get redistributed into the elevator. As you start to climb, as Dennis just showed, the the counterweight is being pulled down. That takes energy, and part of this elastic energy is going to go into contributing to pulling the counterweight down. Later on, as the climber is higher up and the counterweight is moving back up, we're going to have to restrain the bottom part of the tether, and that's one of the places where this energy is going to go. But all this depends on how you climb. So look at the panda that I put here. He's climbing the space elevator, and he's got various ways he can choose to climb. The first approach, he'll have his feet clamped against the tether. He'll reach up, and he'll start to pull on his arms. That will cause the tether between his feet and his hands to contract. So he'll be, kind of releasing that elastic energy. Once the tension in the segment of ribbon between his hands and his feet has reached the same tension as the bottom, he releases his feet, brings them up, clamps his feet together, and then he repeats the process. So in this case, there hasn't been any energy dissipated, and this is kind of the ideal case. Option two, the panda, once he's got reached up and grabbed the tether with his hands, instead of pulling down on his hands, another thing he could try is to slowly release pressure on his feet to transfer load to his hands. If he does that, at some point, the bottom part of the tether, where it's touching his feet, is going to start to slip. And in this case, the panda is going to get rope burn on his feet because a big chunk of energy, elastic energy, is going to be released as heat as it slips by his feet. So what's going to happen when we're using wheels? Which one of these two situations are we in, or are we in something intermediate? So to think about that, let's consider a piece of tether that is clamped between two rollers. And here I've got 3 different pieces of tether clamped between pairs of rollers. And let's put ourselves in a reference frame that's moving at the same speed as the roller surface, non-rotating, but it's kind of moving along at it's pretty much stopped. And in this reference frame, if you take a little, if you were to draw a line on the roller, that line is moving along with you. Hopefully, in this reference frame, there's a piece of the tether that is motionless. If that's not the case, then your tether is completely slipping relative to the wheels, and you've got other problems. So here I put 3 different hypotheses with 3 different pink areas showing where the no slip zone is. So this is the area where there is no slippage going on between the roller and the tether. Now, because the tether is getting shorter as it goes through the roller, because tension is being released, around the no slip area, there's going to be motion. And so that's shown by these blue lines. Tether material is going to be sliding towards the no slip area. Now, again, remember, this is in a reference frame that's motionless or close to motionless. It's not in a reference frame that's moving up with the climber. And so you would see tether material going towards the non-slip zone. And that tether material is going to be slipping relative to the wheels. And so it's going to be causing a force, and that's the purple line on the wheel. Now, action reaction says that the wheel is going to be exerting a force on the tether, and that's the yellow lines. Now, if I look at the image on the left, I have an upwards force. Now, we all know that the climber is pushing down on the ribbon, and so that can't possibly be what goes on. In fact, what goes on is the situation on the right, where the no-slip zone is at the top of the contact area. And so that's the main thing I want to get out of here, non-slip zone at the top. All right, so now we can go do a power balance and try to determine how much power is being released as heat in this friction. And so the heat is equal to the sum of the power we're putting in using the motors, plus the work of the 2 tensions above and below, plus the elastic power that's being released. From the previous slide, we were able to determine that the power going in is V1, the speed at the top of the climber, the speed at which the tether is coming in, which is different from the speed at which it's going out because of the tether contraction. And so that power coming in is V1 times the difference in tensions. So when you crank the crank, you end up with this formula down here where the power coming out of the heat is equal to the difference in tension between the top and the bottom of the climber squared times V0 over 2EA. Now you can compare this with the elastic energy that was released, or the elastic power, and that's not the difference in tension squared, but this is the difference of the squares of the tensions. Subtle difference, but it makes a huge difference in the end game. If you had a descending climber, you could go through the same exercise I went in 2 slides ago. You would find that the non-slip region is on the bottom. And so in the case of the descending climber, the power that you're getting out is V2 times the difference in tensions. And so V1 is greater than V2. And so the power you put in when you're climbing is more than the power that you take out when you're descending. The heat power is going to be the same in both cases. And if you're doing a climber simulator, what you probably want to do is when you're going up, you assume that the speed of your roller corresponds to the speed that tether's coming in. When you're going down, it's again the speed at which ribbon's coming in, but that's a different speed because it's the one on the lower side. So in practice, we don't have just one pair of rollers. We've got multiple pair of rollers, and that helps a lot. When you have multiple pairs of rollers, each pair of rollers just sees the total difference in tension divided by n. And so if you now calculate the heat, you're going to have n times the dissipation that you would get for one stage in which the difference of tension is delta T over n. So you have an n here, you have 1 over n squared here. And so the result is when you have n rollers, the heat is going to be the heat you would have with 1 roller divided by n. So this is great. That means if you have n roller pairs, n times less loss. And so for the reference design, I forgot to say it before, we had 400 kilowatts of heat with only 1 roller pair. Now we're down to 40 kilowatts, which is still high, but more manageable. Now, the type of drive you use is going to change the how much heat is released. If you have a pinch drive with n wheels, you're going to have n over 2 independent contact points. And so the factor here will be n over 2. If you have a capstan drive, you have n independent contact points. And so you'll actually get divided by n. Now, if you have this concept that was shown yesterday briefly and during the discussion period, where you have something like a capstan drive, except you've got contacts between each of the roller pairs, now you've really got only one independent contact area. And so you don't get the 1 over n. So this configuration is actually really not a good idea for friction, because it's going to dissipate a lot more energy than the other ones. As the number of rollers goes to infinity, we end up in the ideal situation that I was talking about at the beginning, where no heat is dissipated at all. But of course, the n going to infinity is a lot. One thing I wonder about is whether there's a practical way of doing that option 1 Panda drive, where you don't have a bunch of independent rollers, but you still manage to avoid heat dissipation. Won't go into the detail of this one, but I just wanted to say the capstan drive isn't quite as good as what I said in the previous slide. It's not twice as good as the pinch drive, because you don't have the same delta T between each of the roller pairs. The delta T decreases exponentially as you go down. The bottom line is the capstan drive is probably about 70% better than, sorry, not 70% better. It's 70% of the heat dissipated in the pinch drive, or less. I did a little bit of modeling of this. I'm not going to talk in too much detail about this slide, but basically this was a simulation where I have a climber climbing. There's 5 roller pairs, and I'm looking at the heat going into the ribbon and the roller, and then being dissipated using via radiation. I looked at various tether thicknesses, 1, 10, 100 microns. And in one case, I considered heat dissipation from the tether only. In the other case, I considered it from the tether and the roller. And what we see here is, if we're not careful, we can get ourselves into a real bind, because we have very large delta T's on the tether, and the bottom rollers will be seeing temperatures that will probably cause trouble for the bearings. On the other hand, with careful design, it looks like there are some configurations where things are manageable. So this is a problem we'll have to think about and manage, but it probably is manageable. So some people ask me, Larry in particular, why don't I see glowing hot tethers in climber competitions? Well, the reason is really simple. Like I said, this graphene is pretty magical material. If I plot it on an Ashby plot, it's way out in the corner out here on its own. And in particular, if I look at a line of constant max volumetric energy at failure, that's a line like this. So any, if I draw a line like this, all the materials on that line are going to have the same maximum volumetric energy at failure. Graphene is in a category of its own. It's about 10x higher than the next best thing. And that corresponds to, so 10x higher in strength, and that's going to correspond to 100x higher in energy. And so, something that might be a 10-degree difference with an elastomer will now be a 1,000-degree difference. And that just completely changes the picture. All right, let's move on to the next topic. This is going to be about wrinkling going through the rollers. Looking through the ISEC climber tether interface study report, I saw this picture where the ribbon is a lot wider than the roller. And that got me worried that there might be stress concentrations down in the corners here. So I did a little finite element model to try and understand what that would be like. So this is a piece of tether in which I've applied a line load. There's some stress concentrations down here in the corners like I was expecting, but they're manageable. What I hadn't been expecting to see, but it's obvious in retrospect, is we've got compressive stresses down below the tether. That can be expected. The tether is highly stressed above the roller. Down below, it's not. And that means that because of Poisson's ratio, the tether is going to get wider as it goes through the roller. About 1.8%, if I have the right number here, 0.2 for the Poisson's ratio. There's still some debate on what that number actually is. So what does that mean? If I have a nice flat ribbon coming into the first roller, it'll go through that first roller, and it's going to buckle. The ribbon is very thin, and so there's almost no resistance to buckling. It's going to go and fold create these wrinkles. Then it comes to the second roller, and now we're going to have a problem because the second roller is just going to come in and crumple those wrinkles and potentially produce creasing. And also, that finely calibrated distance between the rollers might be suitable for a flat ribbon, but it's not going to be suitable for this crinkled ribbon. So does this really happen? I did a little experiment. So here you can see me standing on a chair with length of pipe, two masses, one large one, one small one, and a rubber band going over the top of the pipe. And so I'm then going to turn the pipe to make the small mass go down and the large mass go up. And what we'll see is that we have crinkles that form. And so this does indeed seem to be something that will happen. And then the question is, what will happen when the second roller comes along? And I don't have a setup for that yet. So this actually is something that people in the film industry are very familiar with. They have plenty of problems with buckling and crinkling of their films, and they've come up with solutions that are called spreader rollers. So basically, spreader rollers have various schemes that they use, such that when the film goes by, the film gets pushed outwards to try and restore flatness. So it will go over a roller. It might form some wrinkles, but then it goes through the spreader rollers, and those get evened out, and then you continue processing. So there's a lot of little different concepts here. A lot of them use flexible rollers, and at first I was thinking that would not work at all, because in the space elevator we've got very high loads put on our rollers. Thinking about it more, though, I think that these might actually be able to work as long as they are not the main rollers. So these would be rollers that you place between the main rollers of the elevator that are just there for this spreading purpose. So they don't have to carry very large loads. And I think if we're using them in that way, the space elevator gets climbed in a week. I suspect that some of these rollers get used for much longer periods of that in factories and would be able to survive our conditions. All right, let's move
Blaise,
on.
I got so absorbed in your talk, I forgot to mention the time. You're 2 minutes over now.
Okay, well, the next one's going to be fast, and then I'll be done.
Okay.
So the final one is transverse buckling under twisting. So in this case, I've got this little video here that shows what happens if you put a ribbon in tension and twist it. So initially, you have a helical form, but then there comes a point where all of a sudden, boom, there's a buckling that happens, and the ribbon folds in on itself. You can kind of see it on this one. It's a lot more visible here when I take the wider ribbon. And here, the ribbon, rather than staying in a helix, goes and folds up. So this could be a problem. Will the fold be sharp enough to damage the ribbon? Will a climber come along and roll over this folded area, potentially causing damage to the ribbon? If this happens in the area where there's space debris, is the now much narrower ribbon going to be more vulnerable to debris impacts? So it turns out this is also something that's been studied before. And there's a whole ecology of buckling that can happen with ribbons. In our case, there's only this one particular one that is relevant, called transverse buckling. And I'm expecting it to happen at about 1.3 turns per kilometer. So that's the order of magnitude, turns per kilometer. And so we have to be careful not to twist the elevator too much, or else we start to get in these buckling modes and potentially some of the problems I've been showing here. This is a video that shows what happens if I have one of these buckled ribbons and I start rolling it up, which kind of simulates what a climber would be doing. As you can see, the fold totally gets rolled up with the onto the ribbon. It doesn't flatten out when it gets to the roller. So here again, I'm hoping the spreader rollers can help us. If we put a spreader roller before the main roller, hopefully we can avoid the fold getting brought up. So a few final thoughts. If the ribbon is cambered, to be more robust to space debris. We don't even need any buckling. Right at that point, as soon as you start twisting, the ribbon will start to fold. I'm expecting this to really be a problem all the time. There's various causes of twisting. The one I'm most worried about is the wind. There's lots going on in the atmosphere, and I'm expecting that the wind will be causing all kinds of twisting. We've already talked about how bad this is. Solution directions. I think spreader rollers are going to be our friends here. The climber will probably want to have ways to control itself in azimuth in the atmosphere, probably aerodynamic surfaces. And once you're in space, gyros, reaction wheels, thrusters, something will be needed. And maybe we want to put in stiffening ribs the way Brad had them, so that the ribbon tends to want to maintain its shape. All right, so I've walked through 3 problems that hopefully we'd be able to tease out in climber competitions. And my suggestion would be, hey, let's maybe do the climber competitions with rubber bands instead of doing them with Kevlar, so that we can start to see at least the 2 second problems I showed. The first one, I think is going to be really hard to get without having a material similar to graphene and under stress as close to its breaking point. All right, any questions?
Thank you. Your little demonstrations certainly drive things home. I mean,
yes, those were a last-minute addition. I saw those bands sitting on my desk, and I'm like, oh wow, I could actually try this. It adds a lot.
do you have any stiffer materials you could try it with?
Not currently.
Yeah, thanks a lot, Blaise. You've completely horrified me.
Horrification causes action, so this is good.
Other questions? Yeah, this is great. It's a whole new area we need to look at. All right, if there are no other questions.
Well, I got my hand up, but
Oh, sorry. Go ahead, Steve.
yeah. Well, for the last 2 presentations, I'm wondering if you start playing with the initial tension in the tether, if it changes a lot of this. Like if you say down at the sea level, there's like so much tension in the cable or tether to begin with that you have to manage, that would it take out a lot of these events that we're seeing? And if so, at what point does that tension have to be to mitigate a lot of these issues?
So I think tension can help with the heating problem, like with the friction. If you were to make the ribbon a bit too wide at the bottom, well, actually, so first, once you're higher up, the release in tension is less. So there's a smaller fraction of the elastic energy that actually gets released when the climber climbs. And so I think the heating problem there is better. The worst case is when you're down at the bottom and really going through the whole, from completely in tension to almost completely release tension. And so you could help that by having a little bit too much tether down at the bottom to make that delta T smaller. So I think there are some tricks you can play. I'm not sure you're going to need to. I don't think that that differences in tension will necessarily help with the other 2 problems, though. The buckling when you go through the roller, it's really just well, no, I guess if this one also gets better as you go up, because the fractional change in strain is less, which means that the amount of increase in Poisson ratio is less. The twisting one, I don't think the tension will make any difference. Actually, more tension will make things worse, because there's more force trying to make the edges of the ribbon take a straight line rather than follow a helix.
Blaise, can I ask you? Oh, good. Sorry.
Do you assume that in a 5-pair climber that there's an equal distribution of load in every wheel pair?
If it's the pinch drive, I think that is what we would want to do. Yes. And our motor control is going to have to be designed in such a way that this is the case. Because we've got
what I've seen from finding element analysis of a climber that isn't climbing at all is just from flexibility in the mechanical structure, it doesn't distribute load equally.
So if you are applying the same torque on all of your motors, I would expect that load to even out naturally. Because the torque in the motor is going to say what the force that that roller pair is applying to the ribbon is. And so you'll have roughly the same force on each roller pair, and that means you're going to have roughly the same delta T on each one.
But that's what I'm saying, especially when I applied a payload to the middle two sections of structure of the 5-pair climber, the bending that goes on where the climber is distributing the load from the payload changes the load at each roller. I mean, maybe you can compensate for that with the motor controller, but there's going to be some kind of bias built in from the shape and structure of the climber.
So how? Okay, it's not clear how to me that works. I mean, I think I'll stand by my argument that if you're running the same current through the motors, you're getting the same torque, and that should even out the loads.
I agree with Blaise that would be the case. What I think you're looking at, Larry, is you're assuming that all the rollers have the same rotational rate, and then you would have a difference in the loads, but they'd each be turning at different rates because the undeformed length passing through the top of the tether would be longer than the undeformed length below the tether. So they need to roll at different rates, and the torques would be the same.
Yeah, that's absolutely right. Like in the, I was showing you have V1 coming in and V2 coming out, and at each intermediate stage, there'll be an intermediate velocity. And those, that velocity stepping down in each roller pair is key to getting the 1/n reduction in temperature. And, it's what will naturally arise if you have the same torque on all the motors.
Let's go to Adrian and then into the break, please.
Yeah, thanks, Dennis. Blaise, great presentation. Thanks. Just a quickie. In the pinch roller model you've got, and this is the current one that Larry's working with, do you have a feel for the sort of temperature rise on the material of the tether at that point?
So I think it really depends on the thicknesses of the tether and that kind of thing. So if we go back to the model, let's see, if it's 5 stages, and I did this a while ago, so really I would have done 10 stages if I was doing it now, with a 10 micron thick tether. Probably this purple line is the most relevant one, and so there we're getting roughly 300 C rise in temperature from the input to the output.
Oh, great, thanks. So it's not huge from my point of view. Yeah.
I think the tether will be fine. I'm more worried about the rollers. And
I was more concerned about the tether losing strength as the temperature increases, but a few hundred degrees is neither here nor there, so that's all right.
At what temperature would you get worried about the tether?
Probably going up above 1,000, 2,000 sort of, but we're getting to the melting point of the titanium rollers anyway, so
Okay.
It's not a huge issue.
Okay. Yeah, I think the bearings are probably your limiting factor there.
Yeah, you're probably right. Yeah. Thank you.
Did you take thermal expansion into account in that plot?
This does not take thermal expansion into account. I don't think it makes much of a difference, though.
All right, thank you.